computation ended up accepting, and it rejected if they all ended up rejecting. Well, and then we proved that, yes, okay, we have all this descriptive power in non-deterministic finite state machines, but it really was no more powerful than deterministic finite state machines, because any non-deterministic finite state machine could be converted to a deterministic finite state machine. So the class of regular languages that were accepted, the class of languages that were accepted by deterministic finite state machines and non-deterministic finite state machines, those were the same. Okay, so it seems sensible that we would want to explore the same question in the case of Turing machines. We would want to define what a non-deterministic Turing machine is, and then ask, does a non-deterministic Turing machine have more power than a deterministic Turing machine? Is the class of languages recognizable or decided by non-deterministic Turing machines, does that strictly contain the set of languages that are recognized or decided by deterministic Turing machines? In other words, so let me specify what a non-deterministic Turing machine is, and then we'll get into the question of equivalence. So in a non-deterministic Turing machine, so we know what we have to do to specify what we call a Turing machine. So if I say Turing machine, that would usually mean deterministic Turing machine, although sometimes by context, if the context is absolutely clear, it might be a non-deterministic. But for right now, I'll try to make that distinction always explicit. So we know what we need in to specify a deterministic Turing machine. It's the 5 or 6 things that I put up before. We need the input alphabet, we need the tape alphabet, we need the start state, we need to know what the accept state is, we need to know what the reject state is, and then the most important thing of all is we need to know what the transition function is. Okay? So this goes to So this is the basic information you need if you're going to specify, and this is many of them, of course. Well, this represents all of the different transition. This transition function, which contains all of these different transition possibilities. For non-deterministic, just the same way that we define non-deterministic finite state machines, what do we now want to do to define a non-deterministic Turing machine? Yeah. This is the power set over here. So this is some subset of this triple. Okay, this is the triple which says state, what are you going to write, and where are you going to move. And so this is saying, if I'm in state, let's say 7, and I see a B on my tape, okay, then instead of this one thing that I'll necessarily do, there may be several. Maybe I move to state 9, and I write say a Z, and I move right. Well, that's one rule. But another one would be to move into state 15, write a Q, and move left. Okay, and there may be more than 2 possibilities. So there are choices. But that's the specification of a non-deterministic Turing machine. What does the computation of a non-deterministic Turing machine actually do? Well, it does pretty much what you expect it to do based on all of what we did when we were thinking about non-deterministic finite state machines. That is, as the computation of the non-deterministic Turing machine proceeds, when you're at a point, when the Turing machine is at a point where there are choices, the Turing machine replicates. If you have 2 choices, then you have 2 Turing machines. One of those Turing machines takes that action, goes into state Q9, writes a Z, and moves right on the state. And the other Turing machine, the other copy, or replicate of that Turing machine, goes into state Q15, writes a Q, and moves left. Okay? And if there are more than 2 choices, then we replicate into more than 2 different Turing machines. Now, each one of these replicates can spawn off additional replicates and so on. You can get a large tree of possible Turing machines, replicated Turing machines, and different computations that are happening along different paths in that tree. So, so here's the sort of picture, or I'll maybe call it a cartoon, of a computation of a non-deterministic Turing machine. It's got one machine is starting, and then it hits a place where it can make 2 different choices, and that replicates into 2 machines, and then this machine, in this computation, hits a place where there are 3 choices, let's say, and so it replicates 3 times, and they each make a different choice. Maybe this one goes on for a ways without this computation goes on for a ways without hitting a choice. It's deterministic, and then finally hits one where there's 7 different choices. Why did I say 7? I don't know. It's a lot of boxes. Okay, 7 boxes. So a tree, you have a tree of computations, which happens when the non-deterministic Turing machine does its computation. Now, in each one of these computations, ultimately, well, in each of these computations, what happens? That computation either hits an accept state or a reject state, or it could go forever. That computation could go forever. So maybe we come down to an accept, and this one ultimately comes down to a reject, and then this one just goes forever. Okay? And never terminates. So we say this, the non-deterministic Turing machine accepts if any one of these Lippitz-Storndorf machines ultimately accepts. Okay, so, and again, this is really the same thing we were saying when we were talking about non-deterministic finite-state machines. Okay, so the non-deterministic Turing machine accepts its input if any of the spawned computations accepts, or enters an accept state. Okay, and it rejects if every spawned computation enters the reject state. Okay, and it goes forever, or it does not terminate. If any of the spawned machines or spawned computations does not terminate. Let me stop there for a minute. Does this make sense? Did I wrote this up this way? No, who said no? Yeah, and why? Yeah, right. So this can't be the end of it, because here I'm saying the non-deterministic machine will accept if one of its spawned computations ends up as accept. Well, some of the other spawned computations might go forever. Okay? So I don't want to say that I want to leave it like this, where it says it doesn't terminate if any of the spawned computations does not terminate. I don't want to... Okay, I've got myself into a grammatical corner here. There was something that I want to change, but I don't need to change it correctly. I have to change the grammar. It does not terminate, first of all, if no computation, no spawned computations accepts. Okay, and some computation does not terminate. Okay. And you could kind of, I think formally you could remove this, and the first two would imply that we accept when any of the spawned computations accept, we reject if every spawned computation rejects. And it's possible that neither of these two things happen, in which case the termination doesn't terminate. And that's where it's written here. Okay. But these two things imply that one. All right, so now we know what a non-deterministic Turing machine is, how you specify one, and this talks about what the computation looks like, and this talks about whether the machine accepts, rejects, or doesn't terminate. So now we can think of the class of languages that are recognized by, well, a language is recognized by a non-deterministic Turing machine, let's give it a name, N, if for every string in a language, we'll give the language a name, let's say A, for every string in A, N accepts the string. Okay. That's what it means to recognize. Now, we talked about different concepts previously. A language A is decided by a non-deterministic Turing machine called N if N recognizes A and something else. What's that something else? Recognize means that whenever the string is in the language, the non-deterministic Turing machine accepts. So there's some computation that can spawn, and one of those computations is going to end up accepting. Okay. A language A is decided by a non-deterministic Turing machine if it recognizes A, which means whenever there's a string which is in the language, this non-deterministic Turing machine will accept. But here I didn't say what happens when there's a string that's not in the language. Okay. So what can happen typically when a string is not in the language? Well, it may reject, or it could not terminate. The computation might not terminate. Okay. So the distinction between the recognizer and the decider is that the computation always terminates. So the and I want here is that if a string, an input string, is not string A, then the Turing machine, the Turing machine, will reject the input. So this recognizer has the possibility that it doesn't terminate. It always terminates when given a string that actually is an A, it terminates by accepting. But here, we have the possibility that, it has the possibility of not terminating. Here, we get rid of that possibility. Yeah.
Is it rejecting the string?
No, the not any Turing machine that's given a particular string just rejects that string, or the computation doesn't terminate. So the Turing machine treats a particular string, or when it's given a string, it treats on that string. When we talk about accepting a language, well, the first time we use that, the book slapped us on the hand and said, don't do that. Always talk about recognizing a language. So a Turing machine, or a high-state machine, or a Turing machine recognizes a language. It means it accepts the set of strings which are in that language. Did that answer your question? Okay, so we have the word accept. That's talking about a specific machine with a specific input. We have the word recognize.
The string is not made and will reject the input. The string or the input?
Okay, yeah, the string. Let's give it a name W is not in A, that N will reject the input W. Yeah, so when I have string here with input, I meant for them to do the same thing. Thanks for clarifying that. Yeah, input and input. Okay, so now that we have these definitions, we can ask the equivalence question again. Now, it was over here before, but all right. We asked about equivalence for multi-tape Turing machines and single-tape Turing machines, right? Again, there's something over there which literally said, if a language is recognized by a multi-tape Turing machine, is it also recognizable by a single-tape Turing machine? We had that question, we answered yes. Now we're going to ask the same question about non-deterministic Turing machines and deterministic Turing machines. So here's a question. If a language is recognized, and what we could be thinking about decider, by some non-deterministic Turing machine, N, is it also recognized